day, ladies and gentlemen, and we meet yet again. I know you probably are feeling exhausted. Uh, you know, Someone commented that I sound a little bit different, and that's because we've been trying to work hard and just make sure that we produce that quality content for you. If you're feeling just a little bit exhausted and you feel like almost giving up, just remember that we almost at the end, and it's just worth sticking it through, making sure that you do your part. They usually say that the pain of discipline is much better than the pain of regret. So rather you stick it out and be disciplined than regret it later in life and say, I could have done this, I could have done that. So I just want to say, as you prepare for your exams, if you're feeling just a little bit tired, if you're feeling just a little bit, exhausted, and you feel like, perhaps this is not worth it, just remember, you will thank yourself later, for putting in the hard work, for making sure that you do your part. Okay. And my prayer is that you really really strike it and do well for your exams, be it your prelims or your final exams, and I promise you will come out of the woods. Okay, so today I just want to look at rates of reactions, and what I'm going to do is just a question from the SCE exam. So this was the May-June exam. Okay, but the content is really the same, and this will be on from the 2018 paper. So yeah, if you haven't subscribed to our channel, okay, please become part of the family, and just make sure that you hit that thumbs up button, just to say, to show appreciation for the videos that we've been producing. Okay, right, so let's get right into the question. All right, so they say we've got two experiments that are carried out to investigate one of the factors that affect reaction rate. Okay, so just a reminder to you, if you haven't actually watched our videos on rates of reactions, in fact, that's one of the popular ones, just make sure to head over there. Okay, just a reminder again for those of you who need help, assistance with either maths or science. Okay, you are more than welcome to email me, and my email is info@mlungisinkosi.co.za, and I appreciate all your comments and your feedback that I'm getting. Okay, but if you really need help, we can try to assist you. All right. Okay. So we're given factors that affect the reaction rate, which is magnesium and dilute, in a reaction between magnesium and dilute hydrochloric acid. They say the balanced reaction below represents the reaction that takes place. So that's that reaction there. So they say in experiment one, okay, a certain mass of magnesium ribbon reacts with excess dilute hydrochloric acid. Okay, so they took magnesium ribbon in experiment one, and in experiment two, they took magnesium powder, the same mass as the magnesium ribbon, and it reacts with the same volume of excess dilute hydrochloric acid. Okay, so the concentration of the acid is the same in both experiments. Now, before I head over to the question, please note that whenever we give you questions on rates of reactions, you're always going to have that, reaction one, reaction two, reaction three. So, in order for us to answer the question on rates of reactions, you must first identify what is your independent variable. So what is it that they changed between the two reactions? Okay, now if you notice on this one, they actually changed the state of division. So in magnesium ribbons, obviously you've got that one chunk of magnesium ribbon, Whereas if you now use, magnesium powder, you just grind it finely, and you just use the same amount. However, you do know what did they change between the two experiment? The state of division of magnesium, right? So in this case, we know that would be our independent variable. All right, now let me not get ahead of myself. They say define reaction rate. Okay, we know this is the change in concentration of products formed per unit time, or you can say the change in concentration of reactants used per unit time. Okay, and I say for this reaction, write down the independent variable. Okay, remember the independent variable, it's what we have changed in the two experiments. Okay, and so the independent variable here in 5.2.1, okay, so that would be the state of division, okay, of zinc, right? Yeah, of magnesium. Why am I thinking zinc? Right, please, I'm just going to shorten it like that. Okay, so that's the state of division. But now, I know this is not asked. So they said to us, if they were to ask us what would be the dependent variable, remember the dependent variable is the rate of reaction, because by changing the concentration, rather the state of division, what will it affect? The rate at which the reaction takes place, right? So that the rate of reaction depends on the state of division. The rate of reaction depends on temperature. Sometimes they give you temperature as an independent variable. Right, so they say the control variable, remember, the control variable is what you keep the same. Okay, there are a number of things that are a control variable. I suppose it's for 1 mark. So what we'll do is that we'll just pick one, but it could be any of the any of the ones that you can identify. Okay, so number one, you would say, okay, what would be the what did they keep the same? It's the concentration of acid, right? So that's the first one. So you can say, well, it's the concentration of the acid. So remember, whenever you are comparing, or whenever you are taking experiments, you must always make sure that you only have one independent variable in order for it to be a fair test. So in this case, it must be only one independent variable. So the only independent variable here is the state of division. So you make sure that you keep everything else the same, and whatever we keep the same, that's the control variable. So I can mention a couple here. Remember the mass of zinc, of magnesium. Why do I keep saying zinc? I have no clue. Uh, yeah, the mass of magnesium. Yeah, you can talk about the shape of the container, whatever the case may be. Okay, right. So let's continue. Okay, so I've picked one here, which was the concentration of the acid. Okay, right. So now they say to us in the next question, right, they say the change in mass of magnesium is calculated and recorded in 2-minute intervals. Both experiments, for both experiments, that is, the results obtained are shown in the diagram in the graph below, not drawn to scale. Right. So obviously, as the reaction takes place, the mass of magnesium, okay, is going to change, right? So because it's a reactant, so you keep using it, it's going to change. So now that is how we're going to measure the rate of the reaction. Now look at this. When we used, look at this graph. This is the graph for experiment 1. When you use magnesium ribbons, it took 16 seconds for the reaction, for the mass to change, in fact for magnesium to run out, because can you see, this is the graph of mass of magnesium, and it gets to 0. So it means that magnesium actually was a limiting reagent. It's the one that's going to actually run out ultimately, right? And then look at experiment 2. Of course, we expect that the reaction rate is going to be faster when we use powder, isn't it? So look at that reaction there. Magnesium ran out in 10 minutes. Okay, so that tells you that it actually took a shorter time. So the reaction rate here is much greater than. Remember, when we talk about the reaction rate, we are talking about in this case the time that it takes to get to the same result, to get to 0 grams in terms of magnesium. Right, now they say use the information on the graph, okay, to calculate the volume of hydrogen gas produced. Now I'm just going to go back a little bit just to show you something there. Okay, so quite important for us to just know how the reaction looks like. So I'm just going to write it down because we're going to need that. So we said magnesium 2-hydrochloric acid, okay, which will give us magnesium chloride, okay, plus H2. Okay, so this is how the reaction proceeds, okay, and you'll see why I needed that information. So now they say to us we should calculate the volume of gas produced in experiment 1, okay, between time is equals to 2 minutes to 10 minutes. All right, so now let's look at how we are going to do that. So look at experiment 1, okay. So the mass change of magnesium at 2 minutes was 2.6 grams, and at 10 minutes it was 0.2 grams. So what do you have there? You've got the mass of magnesium. So what is that? It's the amount of magnesium that was used in grams. Okay, so remember, for us to apply stoichiometric changes, we need to always make sure that it's in moles. Okay, right, so I'm going to say, well, how much magnesium did I actually use? Right, it would be the change that was made there. I started with 2.6 grams, I ended up with 0.2 grams in 10 minutes. So how much magnesium did I use? So the mass of magnesium that I used would be 2.6 minus 0.2, and so obviously that would be 2.4 grams. Okay, right, then I know, let me find out the number of moles. So the number of moles would be mass over molar mass. Okay, we're going to head over to our periodic table. So this would be 2.4. I'm just quickly going to take my periodic table so that I show you there. Okay, so the mass of magnesium, or rather the molar mass of magnesium, okay, there it is over there, that's 24. Okay, so there's the molar mass of magnesium, so that's 24. So we divide that by 24, and that should give us 0.1 moles. Okay, now I want you to please note there, in this case, as we answer this question, remember, so for us to apply stoichiometry, this simply means, in this case, for every 1 mole of magnesium that I use, I am going to actually produce 1 mole of hydrogen. Can you see that? For every 1 of that, I produce 1 of that. And please remember, you cannot do, ratio and proportion in terms of mass. You can only do that in terms of number of moles, right? Okay, so I'm going to say for every 1 I produce 1. So if I use 0.1 moles of magnesium, therefore I am going to produce how much? 0.1. So it means therefore the number of moles of hydrogen that will be produced is 0.1 moles as well. Okay, now note, they said take the molar gas volume to be 25 cubic decimeters per mole. Now, this is the molar gas volume, which is Vm. So now that I've got number of moles, remember now I can use my formula. Number of moles is volume divided by the molar volume. So usually they give us the molar volume at STP, right? It's also given, but remember STP. Okay, let me show you that there. So they usually give us the molar gas volume at STP, which is 22.4 cubic decimeters per mole. But this time around they gave us, so which means the conditions were different. Okay, so we know number of moles. This was 0.1. We want the volume, but we know the molar gas volume was 25. Okay, so obviously we can now get the volume. Okay, so obviously cross multiply. V times 1 is V. 0.1 times 25, that's going to be 2.5. Remember, this is going to be cubic decimeters. Okay, right, so our volume would be 2.5 cubic decimeters. I hope that makes sense. All right, now let's go to the next question. So in the next question, they say calculate the initial mass of magnesium used. Okay, so what are we looking for? We're looking for that initial mass, right? Used in if the average rate of formation of hydrogen, look at this now. They're giving us the formation of hydrogen, okay, was 2.08 moles per cubic, moles per second, okay? So they are giving us a rate of reaction and they want to find out what were our initial moles, right? So, so all right, it doesn't matter which one we actually use, okay? So, did they tell us? Okay, they said for experiment 2, right? So for experiment 2, if you don't mind, ladies and gents, I'm just going to bring this over to this side and answer it this side. So for experiment 2, what we're simply going to do is just say, all right, so now we know the rate of reaction, okay? So rate of reaction is equal to the change in. Now, please, I want you to see that change, that rate is measured in moles per second. So it means it's important for us that the change there, we must actually say it's change in moles divided by the change in time in order for us to use that rate of reaction. If it was in grams per second, then I can use those grams. But in this case, I'm going to have to find the moles at the beginning, moles at the end, and so on and so forth. Right, now, so what I'm going to do, we know what the rate of reaction is, okay? What is our rate of reaction? It's 2.08 times 10 minus 4, okay? Times 10 to the power minus 4, okay? So in this case, it's going to be moles final, okay? Minus the moles initial divided by time final minus time initial. Let's try and see there. All right, so in this case, if I was supposed to use those masses there or those amounts there, right? Remember, I would have to convert them to moles first. However, in this case, because I'm looking for this one here, and I'm going to use the one at the end and it's 0, okay? So if it's 0 grams, it's going to be 0 moles, right? So I'm going to look for moles. So moles final is 0, okay? And my moles initially, okay, it's the amount that I'm looking for, right? I'm looking for those initial moles divided by what was our time final. Our time final was 16, but remember they said moles per second, right? So meaning that I'm going to have to convert my time from minutes to seconds. So my final time in experiment 2 was 10, okay? So what is 10 minutes? Okay, so that's 10 multiplied by 60. Remember, there are 60 seconds in a minute. So in this case, my time final would be 600. Okay, whereas my time initial, okay, when we started, our time was 0. Okay, just to also just be mindful, please remember, ladies and gents, if it's a decreasing function, okay, if it's a decreasing graph, remember that our rate of reaction is going to be negative. Why? Because our the change there, it's a negative change, right? That's just a point to remember. Okay. If it was an increasing function like that, okay, remember that would be a positive change because you are increasing every time. Here you are decreasing as time progresses, right? So I'm going to make my rate of reaction negative there. Okay, so that's minus 2.08 times 10 minus to the power minus 4. Okay, so all we need to do now is find out what those moles are. So 600 minus 0, that's 600 multiplied by that value there. Okay, so let's do that quickly. Um, I'm sure you've got your calculators going already. Okay, multiplied by 600 and I get a value of 0.1248. Okay, so let's say 125, right? Okay, so I find on the other side I've got minus my moles, which is going to be negative 0.125. So it means that my moles initial would be actually 0.12, well, 1248 moles. Okay, if I want to be very specific. But please remember, they said they were looking for the initial mass. So that's the reason I'm not actually going to leave that to round it off just yet. So I'm looking for the initial mass, right? But what do I have? The initial moles. So please remember, we know that number of moles, once again, it's mass divided by the molar mass, okay? So we've got the number, we're looking for the number of we're looking for the mass rather. So in this case, I'm going to substitute that number 0.1248, okay? I'm looking for the mass. Okay, but remember the molar mass of magnesium was 24, right? All right, so I'm taking that value, multiply it by 24, and what do you have at the end? Okay, I have 2.99, okay, 52, so we just might as well just say it's 3. Okay, so it means that our initial moles was 3 grams. Our initial mass, that was 3 grams. Okay, right. All right, so we've reached the end. So they say use the collision theory. It's always going to get there, right? To explain why the curve in experiment 2 is steeper than that of experiment 1. Okay, so we can just simply explain that in a simple way and just say, well, in this particular case, when we use magnesium strips, right, they have a smaller surface area. So you can say magnesium strips have a smaller surface area. Okay, so Mg strips, okay, have a smaller surface area. I'm just going to abbreviate it SA. Of course, you're going to write it out in full, right? Whilst magnesium powder have a larger surface area. So you think about it, right? So if I have it in powder, obviously it's spread out more, okay? In this case, so magnesium powder has a higher surface area, okay? So magnesium powder, oh yeah, should have said smaller here. All right, so it has a smaller surface area. Magnesium powder has a higher surface area, right? And we know in this case, reaction rate increases with surface area, right? So in this case, with magnesium powder, the number of collisions per second will increase. So more collisions will per second will take place with magnesium powder, and thus will increase the reaction rate. I am quite lazy, ladies and gents, to write all of that down, but I'm sure you understand that, right? Yeah, so just remember that part you always need to get to the point where you talk about the number of collisions per second, okay, because that is what ultimately increases the rate of reaction. So yeah, I think we've reached the end. 17 marks that we would have had on the back. All right, so in this case, that's how the cookie crumbles. So, ladies and gents, please don't forget to subscribe to our channel. All right, and I hope to be seeing you once again. And please keep working hard. Remember, we did say the pain of discipline is much better rather than the pain of regret, right? So as you keep working hard, just make sure that yeah, you also tell others about our channel, okay? Right, and I'll see you guys next time. Sharp, sharp.